It's a real joy and pleasure for me to join all of you today and all of our colleagues across ocean, weather, climate, GIS, data professionals. Everybody is gathering at the conference today to talk a little bit about, as Dawn said, the needs for a greater understanding across the Earth system, with a focus on, in my talk, interfaces of the oceans, atmosphere, sea ice, and humans. As you said, we're moving into this decade of ocean science. So we also recognize that as the largest component of our Earth system, the ocean can be a powerful stabilizing force. So it's even more important to keep it sustainable. As we come together to share our ideas and advances through this conference, I hope we can also be brave enough. I'm going to challenge you to all also talk about where we're struggling, since that's likely to be where we're going to learn the most. Whether it's to solve particularly hard science problems, to curate our data and information in compelling new ways for decision makers, although Dawn just showed us a lot of great examples, but also to ensure that our services reach all who need them to truly thrive and be resilient. Next slide, please. I come to this community as somebody who became exposed to the power of the intersections of atmospheric science and oceanography primarily through my career journey. I've always been driven by the joy and satisfaction of moving applied research into operations, particularly with analyses and prediction. First part of my career, I worked on weather model post-processing and statistical analyses at the Meteorological Development Lab. In the upper left here, you can see a picture of a digital forecast database graphic of dew point forecasts. MDL is also working on wet bulb globe temperatures for heat health to support a lot of our heat health initiatives. It was also a thrill for me to have a front row seat as we entered the era of ensemble prediction to estimate uncertainty. Of course, this is now foundational to the forecast process. So I was really steeped in the challenges of atmospheric prediction as I began my career, and actually with a focus on a relatively short time horizon. Predictions at the time when I started, we won't say how many years ago that was, we were excited if we could get our day 5, 6, 7 forecast to be as accurate as days 3 and 4. And it was a big stretch to try to push out to days 10. So we've come a long way since then. Next slide. So as I moved into joining the National Ocean Service, I certainly expanded my horizons deeper, literally, as I was able to join them in supporting major enhancements in hydrography and ocean mapping at NOS's Office of Coast Survey. Of course, the visualization tools and data services, some of which John showed, are really revolutionizing what we can see and understand in our oceans. This is a picture of methane gas seeps overlaid on multi-beam bathymetry, and it was acquired during the Cascadia Margin Collaborative Seafloor Mapping Project. Next slide. Of course, pushing the ocean prediction boundaries, which is a lot of my work at the Ocean Service, really helped me appreciate the oceans of fluid with a different time signature and a different system memory than the atmosphere. So whether we were working on storm surge modeling, here's a picture from the global AdCirc-based extratropical storm surge forecast system that NOS runs, SDOFs, or harmful algal bloom predictions. This is a picture of the Gulf of Maine Alexandrian prediction from last summer. The intersection of the atmospheric and oceanic flows and conditions were really unmistakable, whether it was the longer term ocean circulations and surface temperature flux influencing the atmosphere above, as certainly happens in our hurricane systems, or whether it was the shorter term atmospheric winds driving the waters in terms of surges, or the surface temperatures and winds driving where the blooms of HABs are forming. So today I want to talk a little bit about the importance of bringing new perspectives, new observations, new analytics, new predictive tools into a better way to understand the intersections of the ocean, air, and ice. Since this is likely where we're going to unlock new understandings that can help us more accurately and reliably predict a large range of ocean, weather, water, and climate phenomena. And these predictions are what our stakeholders are asking from us to meet the really critical challenges that our society is facing. Next slide. So speaking of challenges, let's look at what we're experiencing today across the United States. Unfortunately, in 2020, we set a new record with over 22 weather climate disaster events with losses that exceeded $1 billion. Through September of 21, we've had 18 more of these kinds of disasters. And these are events that are fueled by regimes when we think about the ocean atmosphere circulations. For example, in the West, we've had persistent drought and the extreme heat wave, but then we also had heavy flooding back in January. Between 2020 and 2021, there's been 18 landfalling tropical storms in the Atlantic basin. The 2020 fire season was also record-breaking. We saw 5 million acres burned, and although 2021 was not quite as large in acreage, the number and severity of fires was extensive. I know from the Weather Service, we had a record-breaking number of 210 missions completed where our incident meteorologists went out on site to the fires. Also, one of the things I want to talk about is the acceleration of these events and changes. As you can see, the average number of events per year has increased significantly. From 1980 to 2020, when we look at that whole span, the average number of events was 7. When we look at the most recent 5 years, 2015 to 2020, the average has moved up to 16.2 events. We can really see this acceleration. So we're living through a time of the intersection of many changes, not just the intensity and frequency of the environmental shifts that are fueled by the climate change, but also a lot of change in technology, in social media, the explosion of data availability. Oh yeah, that thing called the global pandemic. So next slide, please. How does this impact all of us? Well, it's a freight train. Common wisdom from change experts like John Cotter and Thomas Friedman is that the pace of change in society is accelerating, and our humans' natural ability to adapt, shown on the lower blue line in this graph, it's really not kept pace. How many of you have sometimes felt you're standing on this platform with all sorts of trains rushing by? I know I have. Sometimes I also feel like I'm on that train and it's moving so fast and taking me away so fast, I can't really tell what's going on in the environment around me. In this graphic, we can see that there's a growing gap in our ability to keep pace, but there's hope. As humans, we're learners and we can develop new ways of adaptability, and both individually as well as thinking about our policies and our policies around technology and data. I think this is going to be a real opportunity to alter our course. Next slide. The experience of these types of events are leading a wide variety of decision makers, from water resource managers, natural resource managers, agriculture, shipping, our state planners who are trying to make plans 5-10 years in advance in the face of climate change, as well as the clean energy sectors trying to help us adapt to these change. They're all demanding improved forecasts and predictions, not just in the 1 week or 2 week range, but also in that 3 and 4 week range, in the monthly range, sub-seasonal to seasonal predictions, as well as those longer term decadal predictions we get from organizations like the IPCC. They need to be able to make more effective more effective choices in the faces of these changes. So there's a lot of challenges here. We've already talked a little bit about the extreme events and how they're accelerating. Water, of course, presents a challenge for us, whether we have too much, as in the record-breaking floods we had back in 2019 and then just this past January, or the extreme high rate of precipitation that we've had in recent events, like in New York City due to the remnants of Ida and that atmospheric river event we just talked about. There's also the issue of having too little water, where predictions are critical to managing our water supply, as well as understanding those fire risks. And then water of changing quality is a challenge. When we're predicting changes in coastal ocean temperature and salinity, this has an important impact on our living marine resources, and of course, in turn, our food supply, as well as our economy. And of course, there's still the criticality of clean drinking water. So predicting the onset of regime shifts is really vitally important, whether it's flash drought, the rapid amelioration of a drought, the agriculture, power, water resource managers really need to be able to plan for that. And of course, where the ocean meets our coasts, we're seeing large changes in sea levels and fundamental coastal processes, whether it's inundation, erosion, as well as ecosystem regime shifts. So I know this is quite a list, and it's a little bit daunting. We could spend the entire conference digging into the different observations, monitoring and research, process studies, social science, data analysis and visualizations that these challenges are going to require. Next slide. But one thing's really clear. We have to understand these challenges at a different scale. I loved Dawn's pictures that she started with of both the ocean fluid and atmosphere fluid. We have to understand at an Earth system, and that Earth system includes us, right? It includes the humans. This figure comes from ocean atmosphere and climate expert Tony Busalaki at UCAR. And it shows that the ocean, atmosphere, ice, and land are at the center of the work we need to connect out to our understanding of physical conditions, to the biological, chemical, and even human systems. So this is going to be absolutely crucial. Addressing the gaps at the interfaces is going to be one of the ways we can keep a reasonable pace and perhaps start to catch up to that rushing train of change. Next slide. So those are a lot of challenges and stakeholder demands. How well are we doing? I just want to give a few examples across GIS, artificial intelligence, and high performance computing with some of our applications at NOAA in terms of how we're trying to address these challenges. Let's start with ice. Next slide. At a state level, our Alaska Sea Ice program works through the forecast process with a whole variety of GIS tools. As a first step, when we go through the process, we analyze the satellite imagery. I'm going to move from left to right in these graphics. And we analyze that and make sure that we have a good understanding of what we're looking at and where the ice is. The forecasters use this imagery then to provide the most accurate analysis they can for those people that are working and making decisions about how to operate near the sea ice. We focus on creating products of the sea ice concentration and thickness, as well as looking at the sea surface temperature charts. Once we create that analysis, we use a variety of toolboxes to make sure that we can consider the risk and uncertainty of the predictions that we're going to make, looking out at forecasts out to 5 days. Of course, the changing Arctic means that some of the sea ice is less predictable than in the past. So folks are operating on the cutting edge of trying to understand and help their partners anticipate and warn them of dramatic changes in local sea ice. In the far right, this is a graphic that's helping with some of this understanding of uncertainty. This is comparing the output from a variety of models, looking at the output from a model run 4 days prior to the validation. And the red areas are areas where the model under forecasted the sea ice concentration, and the blue where the model over forecasted sea ice concentration. So getting this quick turn feedback to the forecasters really helps them understand what they're dealing with and how the models are performing overall. Next slide. So to talk a little bit more, continuing on the sea ice theme, I wanted to talk about the U.S. National Ice Center. So moving at the national and international level. This is a collaboration at the Ice Center between the U.S. Navy, the Coast Guard, and NOAA, all working together to understand this changing interface of ocean, ice, and atmosphere. The US NIC really appreciates over a decade of collaboration with Esri, and they use a custom extension ArcGIS desktop that we call the Satellite Image Processing and Analysis System, or SIPAS. So you can see a couple snapshots as well from them in terms of this process. First, checking their region of interest. We've got 39 Arctic regions and 13 regions in the Antarctic that are available for the analysts and forecasters. They check that data out, bring the highest resolution imagery in, as well as being able to overlay data such as buoy data, model data, and other algorithms, statistical algorithms, and then be able to produce a final product that characterizes the ice concentration and follows WMO standard codes. Next slide. So I wanted to give a couple examples from the product here, because the whole point of all this hard work in forecasting is to provide decision support to those that are out in the field, some of whom are helping us better understand these interfaces that we were talking about. On the left, this is a GIS-derived product supporting the Pacific Marine Environmental Lab sail drone operations in the Arctic, where they're gathering important information. The sail drone operators, of course, want to be near the ice for their research purposes, but of course, they don't want to endanger the sail drones themselves. The red line in this picture is the ice edge, and the blue is the 48-hour forecast. They're also able to overlay radar imagery and the wind and sea ice drift vectors to help those operations. Similarly, on the right side is a picture of the US NIC products supporting the efficient routing of the Coast Guard cutter Healy through the Canadian archipelago. In addition to ice lines and characterizations, they also have the radar and satellite imagery. Next slide. So moving from ice to ocean and where the ocean's meeting the coast, one constant refrain we've heard from users is they want to be able to interact with our data and to visualize that in terms of how it's going to impact their own community and help them plan and take appropriate action. So NOAA's Sea Level Rise Viewer is one of those great tools that allows this. It provides street level, community level, including landmarks data where they can toggle through different levels of IPCC predictions at the 10, 20, and 30 years into the future, and also be able to bring in different layers of socioeconomic data, flood frequency, vulnerability, wetland loss, and all of those types of things. This is just an amazingly valuable tool for all of those that are working on these coastal plans. Next slide. So from the longer term into the real time, this is another example, NOAA's Ocean Services Coastal Inundation Dashboard. We had an opportunity to really make great use of this just a week or two ago as we had a major East Coast system go by. This is an example where we had heavy rainfall coming through, coastal flooding along the mid-Atlantic and northeast coast. And what's great about this dashboard is the synergy of data we can have here. You can see the in situ tidal gauge information. Those are the pins that you see there on the graphic, as well as the Weather Service coastal flood advisory watches and warnings in the green shaded areas. And underlaying this, though, is that longer term information where we've got minor flood level inundation, areas that are chronically vulnerable to that kind of minor flood when just because of the background of sea level rise. And you can also toggle on a map service for sea level rise as well. So this is a great bringing together and synergy of that longer term information with the real-time event. Next slide. So expanding, Don mentioned the National Water Model Services, expanding there. This has been, I think this community is pretty familiar with the launching of that model in 2016. We've been upgrading it ever since, pretty continuously, most recently in April of 21. So we're now on version 2.1. Having this continental scale water resources model, the high resolution and spatially continuous information, it has just been a game changer for us. It brings those operational streamflow guidance into a wider group of underserved locations because we're able to expand that location so much farther, being able to provide guidance for over 3.4 million miles of rivers and streams, just phenomenal. It's also our first foray into doing high performance computing for water prediction. And so we're pushing the limits there with our high resolution 1 kilometer grid nationwide. Also, pushing the limit on dynamic data services. And we know this is going to be a challenge for us. We have over 60 different data services that come out of the water model. So these services update every hour and are helping us provide our national hydrography data set. So one of the things that we're forecasting is the bank full of flooding conditions that you can see here, as well as the relative magnitude of the river flow that compares to a 40-year climatology. We're also able to provide real-time flood inundation mapping. We've been demonstrating this over the last 2 years. This is really critical for us to provide to FEMA and emergency management community, where floodwater, we can tell them where the floodwaters are going to be and where they're not going to be, excuse me, because this helps their communities decide where to stage response assets. And this is really important for their decision-making process. The FIM flood inundation maps have been demonstrated in the West Gulf and Northeast River forecasts, and we can provide them across the country in real time to partners during events. We're working to make those operational over the next coming several years. One thing for this community to keep in mind is that the quality of the FIM is directly related to the quality of the underlying high resolution terrain, the digital elevation models and the bathymetric information. So we really support the continued acquisition of all of that elevation data and being able to provide that out. Next slide. So moving from fresh water to salty water, I want to talk about another challenge that my colleague Jason Link from NOAA's Fisheries has brought to our attention with living marine resources. Of course, they call the ocean their home, and we've shifted from a period where we've talked about, yes, climate's going to be changing and it's going to impact our ocean and our living marine resources, to now our narrative is it's changing and we need to respond. It's also changing beyond what we've been able to detect in our observation, really challenging us to think through the scenarios that we have to compensate for. We really have a critical need to integrate our climate-induced changes into the decisions as we manage these living marine resources and think about the uses for them. The ultimate goal is to be able to know in advance where the major biological resources or hazards are going to occur, where they're going to move, when they will peak, and how that will impact our economic performance. There's new and expanding ocean use sectors when we think about aquaculture or offshore wind energy that are really driving demand to be able to understand and support the sustainability of these living marine resources. So integrating more frequent, more routine, more comprehensive, better predictions is going to be key. Next slide, please. There's going to be many elements that have to come together to be able to do this. We're going to need expertise, of course, in ocean and fisheries observing, ocean and fisheries modeling systems, as well as system development applications, bringing in high performance computing and other tools and visualizations to help us produce actionable information. So this nexus that we're experiencing now of data computing and predictions is a true opportunity to advance marine ecosystem prediction. Next slide, please. So even these last two examples of the water model and marine ecosystem prediction are talking about how we're pushing the limits. And I want to give a few more examples. Next slide. At the Weather Service, we're continuing to grow and move towards a more public cloud solution for both data access and visualization. So one of the new enhancements we've been working on over the last 18 months is working with NOAA's Ocean Service, their Environmental Response Management application, IRMA, and using that foundation to bring it into a Weather Service GIS layer that helps us add the weather threat of the day. And this is just one component of being able to tee up those GIS services. And as we move forward towards a smart cloud approach, we're trying to make sure we share those databases. One of the challenges, one of the areas where we're producing and finding that we're bumping up against limit is the demand cycle. As we provide these services and as the frequency of extreme events drives demand to those services, being able to seamlessly serve them is really a challenge. We can see just a continuous background increase in these events, but also large spikes. And of course, since it's dynamic service of data, that can be really challenging. Next slide. Another area, I talked before about the subseasonal to seasonal prediction and how so many sectors of our society are asking for improved predictions at this scale. So the question is, can our predictions meet this demand? We've noted this need from our stakeholders, and we've been looking at a lot of large-scale events where, frankly, we've fallen short of the need. We're seeing systematic errors in some of our predictions. And we know that improvements could come from better understanding of the ocean-atmosphere connections. This is an example of the 2011 to 2017 long-standing California drought. And this had been going on, as I said, over the course of years. And yet the drought was busted and broke in a record flooding event. So in just 60 days, we went from a major drought to having that ameliorated. And the challenge is that all our models failed to predict this transition. So the question is, what happened here? What went wrong? There's no one gap from what we're seeing right now. There's no silver bullet. All of our studies have shown that the standard correlations between well understood patterns like the La Nina and El Nino cycles for Southern California and Pacific Northwest rainfall, they're valid. The challenge is they only explain about 1/3 of the variance of California and West Coast precipitation. 1/3. So we certainly can't rely just on that understanding. And we're looking at what the potential role is of other tropically forced teleconnections to really help solve these understanding. We're going to have to do a lot of work to understand these global patterns. And the ocean, of course, is a main source of the heat and moisture fluxes. We are seeing some improvements in large-scale precipitation event predictions. Next slide. Don already mentioned the recent atmospheric river event that happened along the West Coast from October 23rd to 26th. Everything came together here with key moisture source in the atmospheric river, as well as the dynamics to help produce that heavy precipitation. With our partnership with the Center for Western Weather and Water Extremes at UC San Diego Scripps, we've been doing some research together across with NOAA and Scripps on these atmospheric events, and we're starting to see, I think, the fruition of this. In this event, our monthly forecast called for elevated probabilities of above normal precip in the California and the Pacific Northwest. So 1 month out, we were calling for it. In week 2, we talked about the high risk of heavy precipitation in this area. And by week 1, so still a full week in advance, we were calling for isolated areas of over 10 inches of rain. So when you think about it, that's still pretty excellent prediction that we're having. So next slide, we really appreciate the partnership here. And here's some data on it, and you can visualize all of the areas that got such heavy rain. It's a lot of water. 7.6 trillion gallons of water fell in that 72 hours. And one of the challenges is that even though we've got a lot of this water, a lot of it was absorbed into or ran off of those extremely dry soils that were prevalent in the antecedent conditions. Next slide. So we're looking at how do we solve this challenge of those systematic gaps and clear lack of understanding of some of our processes. One is to work towards this march towards a fully coupled Earth system prediction model that I talked about. We're going to have to better understand global circulation regimes, and the ocean's going to play a big part in this. So our precipitation grand challenge is the way we're focusing our efforts. We're trying to do this from mesoscale to subseasonal, and then from seasonal all the way out to decadal, and then be able to translate what we learn into decision support. So the whole idea here is to improve our understanding of predictability, improve process level understanding, and improve prediction systems so that we can more accurately predict the limits and understand where our limits of skill are. So there's a number of different efforts going on here. We know social science is going to play a big role. We have to understand the critical forecast questions that those stakeholders we mentioned before are asking us. We have to improve the availability and assimilation of our ocean observations. This will be critical. And these are going to help us understand and define that ocean boundary layer and the fluxes. We're going to need to trace and understand where the sources of the errors are. And that's not an easy thing. So process studies are going to be key so that we can understand these areas of predictability. And not just across the sea surfaces, but the full upper ocean into that air-sea interface and also the air-ice interface. So while we're acknowledging the necessary emphasis on science here for deep prediction, we just don't want to forget that the user and engagement with the users and stakeholders is going to be key to improving these products. Next slide. We appreciate our colleagues at NOAA Research are improving both the observing systems and then also working on those process studies where the global models and the observational systems are coming together to design fieldwork campaigns that will be able to enhance. Data assimilation is going to be critical as we get new observations and new tools. How do we bring them into the models for those improvements? And of course, satellite data infusion is also going to be critical, as well as tools, analytics, and decision support to help us with visualization. Next slide. So we've seen the demand for improved predictions and visualization tools, and I've talked a bit about where we're meeting that demand and where we're still struggling to improve. But it's important to understand how all of these impact our people and our populations that we're part of and that we're proud to serve. On this slide is a picture of NOAA's new, one of their key websites on environmental justice. Next slide. Certainly, there are excellent tools to help us understand where we have gaps, where are we not meeting the needs of the communities that we're trying to serve. One of the most popular and ones that I'm sure all of you are familiar with is CDC's Social Vulnerability Index. Just a reminder here, darker blues are communities that are more highly vulnerable. Here's a little case study for you. When we look at the Social Vulnerability Index, zooming in on Maine and looking at that small blue to the right, small blue county, that's Wayne County, which is home to the city of Detroit. So this is one of the most vulnerable counties in Michigan. And then if you zoom in, and we've analyzed where are our national products and services, how well are they doing? And if one of the counties is coded orange, that means it's a storm-ready county. We've worked with them, we've trained them on how to be more resilient to storms. Wayne County is not a storm-ready county. We've also looked and worked with our colleagues at Oklahoma University who've evaluated whether or not communities understand and can have good comprehension of our warning system. Again, a deeper green is a lower score. Again, we see one of the lowest scores here. So while we have strong national programs, when you zoom in and overlay this vulnerability, you can really see that we've got some room to improve. We're effective on the large scale, but we need to think differently about how we engage at this smaller scale. Next slide. Here's another example on the West Coast. Take a look back at the large and devastating Thomas Fire and the subsequent flash flood debris flow in Montecito, California. On the left, we've got the CDC social vulnerability indices. You can see the lower, more vulnerable scores in the southeast and northwest sectors. Now, the Montecito, of course, is outside the fire perimeter, but significantly, it is downstream of where the burn scars formed. On January 9th of 2018, recall the fire was December 4th of 2017 when it started, was a very long and devastating fire. On January 9th of 2018, even before the fire was considered fully contained, we had a flash flooding event and a debris flow event. On the right is a before and after of this debris flow. You can clearly see that many structures in the path of the debris flow were completely destroyed and others were impacted. And while one firefighter and one civilian tragically died in the Thomas Fire, sadly, there were 21 additional deaths due to the debris flow. And many of the people who died were landscapers, house cleaners, and other household workers. So it's just another reminder of how important it is to raise awareness of some of these more hidden threats and make that awareness clear among diverse communities. Next slide. Another risk where we're trying to raise our awareness is heat and the concept of heat health. Of course, we understand now exposure to extreme heat can trigger a variety of heat stress conditions, the most severe of which, of course, is heat stroke, but we can also have impacts on respiratory systems. I'm sure many on this call experienced the Northwest heat wave this past summer. It's a hidden killer. It's racking up some of the highest fatalities of any weather extreme event. Happy to say that there's many organizations partnering together to support engagement. So what's really exciting is to see volunteer-based community science field campaigns. So one of the ways we're doing this is NOAA and CDC partnering on the NOAA National Integrated Heat Health Information System. This is providing funds and grants to the Climate Adaptation Planning Analytics who partner with communities. We've been doing this campaign for several years, and the campaign for 2022 is just starting. So if you know someone in a community nearby, please ask them to think about applying and check out the story map. Along the same lines, we're tapping into the Census Bureau's Opportunity Project, or TOP. Here they're funding and helping communities bring together and synthesize data so that underserved communities who might not have the budgets and resources to provide their own tailored information can have access. This is a 12-week product development sprint in the TOP project, so it's really great to see how this comes together. In this picture, we have Jeremy Hoffman, who's a scientist with the Science Museum of Virginia, and Vivek Chandas, a professor at Portland State University, and they're going over maps of Richmond, Virginia, as they plan routes for some citizen science campaigns. Next slide. So I'd like to tell just one quick story that brought home for me this complex challenge of communities that our communities are navigating when it comes to social vulnerability and equitable services. In this case, it's Las Vegas, Nevada, which I got to visit just a week or two ago. And they're dealing with the complexities of affordable housing and extreme heat events. There's 500 miles of tunnels underneath Las Vegas. They're large and they stay relatively cool. So they're an ideal refuge for hundreds of homeless people to escape the heat. However, the tunnels were built as a solution for a different extreme event threat in Las Vegas, flash flooding. So now we have a vulnerable population at risk from a new threat, not just the heat, but now the impacts of flooding that come in heavy rainfall events. And it's making advanced prediction, being able to get advance notice out and make sure that those tunnels are cleared of people, make sure they're out of harm's way, even more critical. So awareness of these inequities and the unique impact that extreme weather events can have is really key. And it's going to charge us to modify the way we communicate, message, and help people visualize these risks. Next slide. So this focus on service equity, coming back to our Earth system circle here, the focus on service equity in these last few examples really highlights how important it is to understand the intersections between the environment and our human systems. I know many of us are inspired by the luminaries of the Renaissance, Da Vinci and Michelangelo. In Franz Johansson's book, The Medici Effects, he talks about the power of diversity and passion to truly move the needle. So here's his quote: when you step into the intersection of fields, just what we've been talking about, disciplines and cultures, you can combine the existing concepts into a large number of extraordinary ideas. That's what we need, extraordinary ideas. I'm truly inspired by the work that many of you are doing to address these challenges. Exciting to listen to the lightning talks. And you're innovatively transforming the way we deliver decision support to all communities. And we're going to need to keep learning how to make these leaps of understanding and turn them into action, as Dawn said, so that our communities can be sustainable, ready, responsive, and resilient. So please keep going. I can't wait to see what you do next. Thank you.